Okay, I'm going to try this a third time. My phone keeps ringing, so I've tried to record this several times for you. All right, we're going to group lesson set 34 and lesson set 35 together. They kind of go hand in hand. It's not all of 35, but I'm going to group the first part of 35 together. What lesson set 34 has you do is they just want to know what is the greatest common factor. And then what lesson set 35 asks you to do is they ask you to actually factor out the greatest common factor. So the first thing we want to do is talk about what is the greatest common factor. A little bit about factors, just like we have talked about literal coefficients and numerical coefficients. If we look at 210x y squared z cubed, that is the same thing as 2 times 3 times 5 times 7 in prime factorization. We have x, y squared is the same thing as y times y, and z cubed is z is a factor 3 times. Now out of that we have numerical factors, which are in red. That's just your numbers, 2 times 3 times 5 times 7. And we have literal coefficients, which are just, or not coefficients, factors, which are just like literal coefficients. It is the numbers, so we have x times y times y times z times z times z. Now if you group both the literal and the numerical coefficients together, so if we group both of these together, we get something called algebraic factors. So we want to be able to come up with the factors per term, and we want to find the greatest common factor. Now the greatest common factor of 2 or more terms is the product of all the prime factors common to every term, each to the highest power that it occurs in all of the terms. So what that basically means is you're going to be, this is the wording that's in the book, but what I would be careful of is the least common factor. You want the smallest of each factor that occurs in every single term. So as I look at this particular problem here, if I look at what I have given to you, and I want to figure out what is, I got to erase this here for a second. If I look at this and I want to figure out what is the greatest common factor. So to find the greatest common factor, it has to be in every single term. So if I look at it, I have a factor of a 2, I have a factor of a 3. I should have waited to cross this out. I meant to wait to cross it out. I couldn't remember why I set it up. So what you have is you have a 2, you have a 3, you have an x, you have a y, and an m. So you have all of those all of those factors, and as you look at it, you have this 2, but it does not occur in every single term. Therefore, that is not part of the greatest common factor. We have the factor of 3. Does that occur in every single term? Yes, it does. What is the highest power that it occurs in every single term? Well, 3 to the first occurs in every single term, so it's just 3 to the first. Is there an x in every single term? Yes, there is an x in every single term. And if you look at it, you wanted the highest power in every single term. That basically means you are looking for the smallest power, because you have x squared, you have x to the first, and you have x cubed. The most number of x's in every single term is just to the first because of that second term. Now y is in every single term, and if we look at that, you have y squared, y cubed, y squared. The highest that's, or I should say the most that you have in every single term is y squared. You have at least y squared in every single term. M is a factor only in 2 of the terms, so therefore that does not become part of your greatest common factor. So your greatest common factor is 3xy squared. Now you can look at that.
Call from Norfolk E.
And I'm sorry, I don't want to answer the phone.
Call from Norfolk E.
Let me just pause it here while. Okay, I give up. Third time trying to record this and the phone rings every single time. So I'm just going to take off from where I was at. All right, so another way you can look at it is I have lined each one of these up. And if you want to find the greatest common factor, and I find this easier than using the definition that they have in the book and the method that they try using. Oh my gosh. Just a moment. Okay, it's a good thing I did not start this over for a fourth time because the phone rang again for the fourth time. So I so much apologize for the interruptions. But anyway, as we look at this, what we have is I wrote the factors of every single term. And what I find it to be easiest is to come up with that greatest common factor. It has to occur in every single term. So if I look at these terms, I have this factor of 3. That is part of the greatest common factor. I have an x in every single term. That's part of the greatest common factor. And if I look at it, I have 2 y's that occur, which means that is y to the second power. So your greatest common factor is 3xy squared. Now some of you don't mind looking at this and then picking them out and finding it has to be in every single term, but it's going to be the lowest power that it is raised to. But what gets confusing is the way they write it in the book. It's in the book on the box on page 138. It talks about this highest power, and too many times people want to say that the greatest common factor here is y cubed because that's the highest power. But it's the highest power that it occurs in all of the terms, which is just to the second power, which you see when you write it in this format. Now the part that is continuing into lesson set 35 is what I'm going to write as this remainder part. And if you were to factor out the greatest common factor, what you are left with is the values that are not in every single term. So if I look at the top one, what I don't have circled as groups of occurring in every single term is 2x and m squared. If I look at that second term, what I do not have circled is x m squared. And in the last term, what we are left with is x squared. So this is the full factored form that they are looking for in lesson set 35. The greatest common factor is just 3xy squared. But what you are left with is what is known as the factored form if you include that, which 3x squared y, or 3xy squared times the quantity 2xm squared plus xm squared plus x squared is going to be the full factored form. Okay, so if we look at this example and I want to figure out what is the greatest common factor. Well, some of you are going to be able to say, well, the factors between 8 and 12, the greatest common one is 4. But others of you aren't going to be able to see that. So we're going to expand this out, and eventually you won't have to expand it out. You will be able to just find it without doing that, because you're going to catch on, like I said, it is the smallest exponent as long as it occurs in every single term. Excuse me. So 8 is 2 times 2 times 2. You have z to the 4th, so I'm going to put down 4 z's. And when you start getting larger exponents in a lot of these, this is why you don't want to write it down all the time. But just to get us familiar with the process, I'm going to write it down. We have m squared and p. Now the second one, if I look at this second term, you have 12, which is 2 times 2 times 3. You have z cubed. So I'm trying to line these up the best I can. You have m to the 4th, and you have p squared, which is 2p's. All right, to find the greatest common factor, the greatest common factor would be I have 2 pairs of 2's, so 2 times 2 is 4. I have 3 pairs of z's, so that's going to be z to the 3rd. I have 2 pairs of m's, so that's going to be m squared. And I have 1 pair of p's, which is going to be p. So the greatest common factor is 4 z cubed m squared p. Remember, you want the smallest exponent as long as the variable occurs in every single term. Now lesson 35 is going to say factor out the greatest common factor. So if I factor out the greatest common factor, That is the greatest common factor, but what you are left with is in the first term you have a 2 and a z, and in the second term, there's a minus sign there, you are left with 3 m squared and a p. So here's your greatest common factor, which is what they're talking about in this lesson, but the next lesson asks you to factor it out, which leaves you with this second answer of 4z cubed m squared p times the quantity 2z minus 3 m squared p. Okay, let's look at the next example. And I apologize for the scribble there. I was going to do it a different method, and I thought I better stick with this first method that I have so far. We can talk differently about it in the next lesson. So as we look at this, we want to factor out or figure out what is the greatest common factor. So the greatest common factor is what both terms have in common. So they have 2 to the second power, and 2 squared is 4. So don't write it as 2 squared, just go ahead and calculate that as 4. We have this pair of x's right here. Like I said, there's only one x that they have in common. I was going to write it as squared and then just go with the lowest power, but I figured I better do it this way. So then we have 2 y's, which means y squared. And then I have one of the z's that occurs in both, so then I just have a z. So that's the greatest common factor. If I want to factor that out from the original problem, I would take out a 4. I can take out 1x. If you look at the y's, I can take out 2. You can't take out any more than what is there. And I can factor out a z. If you do that, what you are left with is you are left with x, y in the first term, and your second term, you are left with 2z squared. So we have our greatest common factor and we have our factored form of the expression up above. Now if you were to use the distributive property, you should be able to get back to the original problem. Okay, this last example I did leave it as exponents, and the reason for it is because I did not want to write out 15 p's. So if I look at just the numerical factors, the only thing that occurs in all three terms is 2 to the first power. As far as the x's are concerned, if I were to write these out, the most that I could take out of every single one is just x squared. I do not have 3 of them to remove from the first and the third term. So we're just, the greatest common factor is just going to involve an x squared then. The least or the most you can take out of every single term means the smallest exponent. So if I look at the y values, I can only take out 1 y from this first term. So the greatest factor, common factor, is just y to the first. And if I look at p, I can only remove 1 p from the second term. So my greatest common factor is 2x squared yp. Now if I were to go ahead and factor the entire problem, I notice that if I take out these 2's in the first term, you're left with 2 times 2 times 2, which is 8. And when I use that distributive property, I get to 16. I factored out all of those x squareds. I took out all of the y. And I took out 2 of these p's. So if I take 2 away from I took out 1, I'm sorry. You take out 1 p. And if I take that 1 p out, you are left with p squared. So if I use the distributive property here, you get 16x squared y p to the third. And that is what your first term is right here. Now, if you look at the second term, there is a minus sign, and you are left with a 2. I took out x squared, so if you have 3 of them and you take out 2 of them, you are left with 1 of them. I took out 1 y, and you had 2, so there's still going to be a y left, and I took out p. So using the distributive property, you get negative 4x cubed y squared p, which is what that second term is. And the last term, you brought out x squared, you brought out y, so you are left with a y term, and you brought out p, which leaves you with p to the 14th. And if you were to use the distributive property, you're going to get plus 2x squared. you're going to have y times y is y squared and p times p to the 14.